I'm going to tell you a little bit about solid-state sensors, more from the material side. That's my background. So how do we get them? What makes a good sensor from the materials perspective? I will be joining, let me get my timer on. Yeah, I will be joining the CBPF soon, so you can find me there. But I'm coming from a long time spent abroad. I've been in the Netherlands and now in Cambridge just before coming to Brazil. And I've been mainly working with these solid-state systems, right? I've tried to make this kind of tutorial-like. If it starts to be too slow, if someone starts snoring, I can speed up, yeah? So thank you very much, Danielle, for the brilliant introduction to a lot of concepts that I'll use here today as well. But whenever we're talking about quantum sensors, what we're trying to do is to gain functionality from quantum properties, like coherence and entanglement, to gain sensitivity, right? To be able to perform better measurements. And like Danielle just introduced, this goes into several quantities that you could be focusing on. But in the solid state, we're usually mostly focusing on field sensing. How can we use solid state systems to sense fields? And one of the main motivations to go to the solid state is because it's easier to miniaturize, right, solid state platforms. So some of the measurements that you could think of performing or where could these sensors be useful, of course, in material science and studying solid state physics, they can be extremely powerful tools, right? So these sensors, for instance, they can sense magnetic properties, and they can allow you to map magnetization of different materials really at the nanoscale, right? So you can look at different magnetic domains of 2D, novel 2D materials, but you can also think about looking at magnetic textures that are really sort of at the forefront of the development of physics and magnetism. You can also, if you can sense magnetic fields, you can also sense flowing currents, right? So in the application side, that could be extremely powerful. So you can imagine a system that allows you to map currents flowing through a circuit, right, and to map failure points of an electronic circuit really at the nanometric scale, right? So this is one implementation where they use a quantum sensor that I'll introduce a little bit more in detail to really map the currents flowing through a graphene channel, and they can map sort of the breakdown of ohmic transport in these graphene channel. But not only for quantum for science of materials, you can also think about using these sensors to study magnetic properties at the nanoscale of molecules, for instance, right? So you can think of doing an MR or MRI, magnetic imaging, magnetic resonance imaging, but now at the molecular scale, right? So you can look at individual spin-active nuclei in molecules like DNAs, but also inside cells, and so on and so forth. So you can gain another sort of channel to study biological processes in this way. And then finally, like Danielle just said, I'll reuse one of the figures that he had in his presentation. You can use these systems in now really small devices to map properties of magnetism and as accelerometers and so on, right? So the breadth of applications of these systems is really, really wide, right? So I thought about starting by introducing a few of the material platforms that have been explored for quantum sensing in the solid state. Even though the one that I'm most interested in and where the rest of this talk focuses on is these systems right here. But it's not only defects in solids that have been used, but also sort of more from the device physics. There's some developments in, or very important developments in sort of making new sensors that function at the nanoscale and that use quantum properties in order to do so. So one of the most established one is superconducting devices, right? So these are called SQUIDs, quantum interference devices, and they're made up of two superconducting leads with a constriction in between And now the tunneling processes through these constriction gives rise to a quantum interference process that makes the current that you measure between these two leads very, very sensitive to magnetic field, but also flux and so on. Right? So these are really exquisitely sensitive things, but they need to be fabricated at the nanoscale, and there lies one of the most important challenges. Like I said, they're very useful for mapping magnetic field, magnetic flux, current flow. They offer the possibility of electrical readout, so what you actually read in these systems is the current between these two leads, but because they're based on superconducting materials, they function mostly at the cryogenic temperature limit, right? If you're interested in these, someone who will be joining me at CBPF is Stephanie Marchiori, and she's coming from Switzerland with a lot of experience in these systems. So if you're interested, do reach out to her. Now, if you're interested in mapping electric fields, you can use also nanofabricated structures that are now made up of a quantum point contact, right? So these are systems where you can have the flow of single electrons at a time, and this flow is really, really sensitive to electric fields. So what you gain is a quantum sensor to electric fields. They also offer electrical readout, but they, again, only function at cryogenic temperatures. Once you start to heat these up, then thermal noise starts to take over, and you no longer have sort of this readout of the flow of single electrons at a time. And then the systems that I'm most interested in, and that Sergio has also a lot of work on, and if I forget someone, please forgive me, I'm new to the community, are these defects in solids, and I'll introduce them in a lot more detail through the rest of my talk. And because of their microscopic properties, they are sensitive also to magnetic fields and therefore to current flow. They, in certain conditions, can be sensitive to electric fields, but also temperature, pressure, so on and so forth, right? So, like Danielle just pointed out, these are quantum systems that are extremely sensitive to their environment, and if you can control that very well, then you're able to isolate different degrees of freedom, right? And you're able to sense different quantities. One of their possible advantages is that they offer optical readout, so you can read their information through optical means. You don't need to have electrical connections going in, and they can function all the way from room temperature to cryogenic temperature. So that's one of their I would say, one of their biggest, I don't want to say advantages, but one of their biggest offers, right, is that flexibility in temperature. So these are the systems that I've been working on. These are defects in materials. They can be sensitive to different fields around them. They can be useful for other types of quantum technologies, but really their biggest possibilities lie in quantum sensing, right? So the rest of my talk will be organized like this. I'll tell you a little bit about the NV center in Diamond. That's kind of the prototypical system. It's the one that has been most widely studied, and it's mostly applied today. And it offers really immense possibilities. And I'll tell you a little bit about what are the methods that are being used to sense with these systems, and I'll highlight a few of the most recent sort of breakthroughs that have been shown based on the systems. But also I'll tell you a little bit in the end of why do we want to look for other quantum sensors and other materials, and where to look for these, right? So the NV center in diamond, it's a defect in the crystalline lattice of diamond. Diamond itself, from an optical point of view, it's not a very interesting material, right? It's a high band gap semiconductor, a very good insulator, whatever you want to call it. But the band gap is about 6 eV. It's transparent. It doesn't give you a lot to work on until you start putting defects in its crystalline lattice, right? So once you start adding defects to this lattice, these defects give rise to localized electronic states that function almost like a molecule or an artificial atom trapped in the crystal host, right? In the sort of optically inert crystalline host, right? So now you can use the localized states of these defects as tools similarly with a lot less control to the tools that Danielle has introduced earlier, right? So the most widely studied system is really the NV center. So that's it's a defect that is made up of a nitrogen impurity in the crystalline lattice next to a vacancy, right? And what happens is you end up with extra electrons from the nitrogen and these dangling bonds from the vacancy, and you end up with 6 electrons with 2 unpaired spins that are sort of trapped within these electronic states, right? So the system has a ground state and an optically excited state. You can drive these optical transitions and collect light from its optical decay. And it also has a singlet manifold. It also has a singlet manifold over here, right? And the ground state, like I said, it's made up of 2 unpaired electron spins that are trapped within these electronic states. And what happens is you end up with the spin triplet in the ground state. And this triplet has a zero field splitting that arises from the dipole-dipole interaction between the 2 unpaired spins, right? So these 2 unpaired spins that are trapped within this space, they interact through dipole-dipole interaction. And this interaction is different depending whether spins are aligned parallel to the symmetry of the electronic state or anti-parallel, right? So at zero field with no magnetic field, you end up with the spin splitting that comes from this dipole-dipole interaction between these 2 states. Now, like I said, there's also a singlet manifold over here, right? So that's when these 2 unpaired spins actually pair up. And the rest of the optical cycle of this system is composed of non-radiative spin transitions from the triplet excited state into the singlet manifold and then back. What's special about this system is that these non-radiative transitions are spin-dependent, right? So once you start driving optical transitions within the system, you end up with the spin polarization that arises from the optical cycling between ground and excited state. Right? So optical driving of the system initializes your spin. Yeah? And now this is very special because what it gives rise to is it gives rise to a contrast in fluorescence depending on the spin state of your system. Right? So that gives rise to your optical readout. Depending on the spin of your system, the fluorescence is different. Right? So it emits more or less photons depending on the spin. And that means you can directly relate the number of photons that you collect when you optically drive to what's the spin state, right? So it gives you a direct connection between these 2. Now, what that leads to is to a very natural qubit operation loop where you can use optical transitions to initialize the spin into the bright state. You then can use microwaves to manipulate this spin and perform any type of spin control protocol that you would like to. And then you can, again, use optical drive to read out what spin state you're in, right? So that offers sort of a very intuitive loop for operation. Now, if we want to use that for sensing, one very natural way, which Daniel has already introduced, is to sort of relate the position of the microwave transitions that you can drive between these spin states to the magnetic field that it experiences, right? So you can sort of, you find your microwave resonance, yeah? You park your microwaves here halfway on the slope of this resonance, and you monitor the photoluminescence of your system, so the number of photons emitted per second by your system. And if there's any change in photoluminescence, you can then relate that to a change in the magnetic field that that system is experiencing, right? So you can translate between these 2 quantities. Now, this is the way that this system has been very widely used for sensing. It's not the only way. But this is a way of using a quantum sensor for measuring, but it's not quantum sensing, right? You're still measuring classical properties. You're not using coherence to gain sensitivity, right? it's very powerful, and it allows you to go a million places, but it's not strictly quantum sensing. You're not using any coherent properties of the system. But you can, right? You can still drive, so use spin control operations to actually manipulate these quantum states and use Ramsey type of measurements where you really gain information from the coherence properties, right? So if you want to do that, you can either use Ramsey type interference, which Danielle has introduced very extensively, and I'm very thankful for it, or you can use relaxometry, where you actually measure how likely your system is to relax, right? So how likely the spin is to relax. And that gives you a measure of spin noise, of magnetic noise. So you can use that to detect different types of magnetic noise, and whether paramagnetic or impurities, for instance, are more abundant or less abundant in the environment, right? And that allows you to really do wonderful things. So this is a result from a group in the Netherlands, in Delft, where they use very complicated spin control gates, right? So very complicated spin control algorithms to sort of manipulate the spin of the NV center and then measure back what the likelihood of being in one or another state is, right? So that's what they're doing here. What you have here is a normalized signal that is detected optically and has to do with whether the system is in spin up or spin down, right? After a sequence of operations like this, versus the total evolution time of the system, right? And very clearly, this likelihood decays because the system has an intrinsic spin coherence time to it, right? So that likelihood decays. But what you can see, and what would look like noise to any reasonable human being, they can actually map out into the interactions of the NV center with individual carbon-13 atoms in the lattice, right? So they can use a measurement like this and the behavior that they observe here to actually identify the individual positions of carbon-13 atoms in the lattice. And they do this, I think, in this work up to 27, but they've done that to 51 now. So they can identify individual interactions between the NV center and these carbon atoms. And from the magnitude of that interaction, they can map out the position. So this is actually performing NMR at the local scale, at the nanoscale. They're still doing NMR on the diamond itself, right? So they can see individual nuclei on the diamond itself, but it's easy to sort of dream of how something like this could be used to actually identify, right, individual nuclei in the environment. Now, I won't go a lot further into sort of the details of how you can do quantum sensing using NVs. This review is really established in the field. It's really great, and it really explains in quite a bit of detail, but still accessible, what are the requirements and what kind of caveats are there to measuring and so on. So I really recommend it. If you're curious, have a read. It's really a wonderful, wonderful read. Right. So now, how are these measurements performed sort of in the lab, right? What do you need? Because one of the great advantages, I think, of these systems is that they are quite forgiving in what you're required to have in order to perform these measurements, right? So what you would have is a typical confocal microscope. So what is behind this is a confocal microscope. It's something that is present in a lot of optics lab. It's actually a very forgiving confocal microscope. It doesn't have to be the best out there. But light comes in through an objective, right? And you collect the light emitted by these systems back through the same objective, right? You have whatever you're using to perform quantum sensing over here and whatever you're sensing underneath it or on top of it. And then the last thing you need is something to deliver microwaves. So that can be a microwave circuit that you've especially printed onto your diamond slab, but it can also be just an antenna that you pass light through and that you're able to manipulate these systems. So these are really the required ingredients. And the way in which it's implemented depends a little bit about what functionality you want to have, right? If you want a lot of sensitivity, then you want to collect a lot of light at the same time, right? You want as many photons as you can out of the system at the same time. So you would typically work with an ensemble of NVs, right? So you would typically work with a slab of diamond, that's what is over here, that has NVs spread all over it, where your spatial resolution is now limited by the diffraction limit, right? So as little as you can make your optical spot, but at the same time, you're interrogating a lot of NVs at the same time, and they're sort of all constructively giving out photons and enhancing your sensitivity, right? You're parallelizing your measurement through measuring a lot of at the same time. And then at the other end of the spectrum, if you're interested in really sort of exquisite spatial resolution, then you would want to work with the single NV, because that gives you sort of the ultimate limit of what resolution you can have by scanning that NV around. And implementations of that can be various. So you could also have a slab of diamond, but with very dilute concentration of NVs, where you can identify single NVs, and then you can sort of spatially scan by looking at different NVs. Or you could have something that looks a little bit like it's a microscopy technique that looks a little bit like AFM, for instance, or MFM, if you're used to it, but where you have a cantilever, right? And that cantilever in this case is made up of diamond. And that cantilever has a tip where you have a single NV there at the end. And now you scan that tip around. You scan that tip over your material. And you, at the same time, read out what photoluminescence it gives when you're driving with microarrays, right? And then from that, you can extract what is the magnetic environment at individual sort of points in space, right? Depending on what technique you have, you can get different sensitivities. So that is from a very recent review that is really, really nice. And what they're mapping here is sensitivity versus the frequency of operation. So it relates, again, back to sort of how quickly you can perform these measurements. If you want to operate in the DC limit, right, that's all the way over here. That's where you're sort of measuring shifts in the microwave resonance, the simplest case that I pointed out, which is not technically quantum sensing, but sensing with a quantum sensor, right? So in that range, if you're operating with ensembles, you can get sensitivities of, what does this read here? 10 to the minus 8, that sounds about right. So about 10 nanotesla per square root hertz, right? So that means per second of measurement. And if you're operating with singles, then your sensitivity goes a little bit up, but again, you gain this spatial resolution. And then if you're actually performing sort of Ramsey types of measurements or relaxometry, you can gain a lot in sensitivity. So the state of the art is really here around a picotesla or so per square root hertz. So these can be really, really sensitive, not as sensitive as atomic centers, but they are in the solid state, right? So you can integrate them into devices and so on in an easier way. So I just sort of collected a few of the recent demonstrations of how these systems can be used, just for sort of proof of principle here, right? But like I said, one of the most interesting implementations is looking at magnetization in the solid state. And in this work that is now not so new anymore, they're looking at 2D antiferromagnets. And what they're doing is they're mapping the magnetization spatially, right? And this was possibly one of the first demonstrations that these type of systems have magnetizations that flip up, down, depending on the layer, right? So one of the first visualizations of this. Now, like I mentioned earlier on, you can also map the flow of currents. And in this work, it's a little bit of a different implementation. Like I said, what they have is a slab of diamond with individual NVs spread around, right? So each of these bright points here is one of the NVs. And what they do is they do relaxometry. So they measure, after you initialize the spin of the NV, how quickly does it relax back to its thermal state, and that they can relate to the magnetic noise that is present, right? And they use this in a device where you have the NV, and on top of it, you have graphene with two current leads over here. They use this to demonstrate something that is called Cherenkov instability in the solid state, where you have some coupling between electrons that are drifting in the material and phonons, and that increases the magnetic noise that these NVs see, right? So what you're seeing is that as the NVs are farther away from the lead in the system, they're experiencing exponentially larger magnetic noise, right? And then finally, some of the most recent applications have been in looking for high pressure superconductivity, right? So it's a fortuitous coincidence that anvil cells are also made of diamond. So you can integrate these systems into anvil cells, and then you can use these anvil cells to apply pressure to materials, and some of these materials become superconducting at high pressure, and that's what they're looking at in this work over here. So that's very recent. At some point, I did a journal club when this was still in archive. But they're looking at individual NVs within the anvil cell, and they're sort of correlating the magnetic field that these NVs are seeing to the superconducting transition of this material, right? And through that, because of the Meissner effect, you can sort of see that these NVs experience decreasingly large magnetic field once you reach the superconducting transition. And then finally, I told you these can also be used for biological applications. This is not the first implementation of looking at current flowing through neurons using NVs, but it's one of the last, I would say. But in this work, they're also using a slab of NVs where they grow neurons on top of them, and then they sort of scan their optical readout across the NVs, and they can map out the current that is flowing through neurons once they're given a certain stimulus, right? So they give a certain stimulus to these neurons on one end or the other, and information travels through these neurons through travel of ionic charges, right? And that creates a current. And by reading out the NVs, they can read out the current that is present due to the traveling of information through these neurons, right? I think that the first paper that did that is already quite a few years ago, maybe 2019, 15, could be quite a few years ago. But the sensitivity has really come a long way, right? So here, this is process data. So they use a lot of frequency filtering and doing Ramsey type of sequences in order to get to this type of data. But yeah, they correlate that to the traveling of information through the neuron, right? So it gives you another tool to look at these things. Where do things happen and so on. So you can gain both temporal and spatial information in this way. So if it's so awesome, why would you need other things, right? Where are the limitations of these? So one of the first limitations especially for solid state, for the study of solid state systems, is that these have limited bandwidth in the sense that they don't operate at arbitrary magnetic fields, right? Because of the intrinsic symmetry of the NVs, they have a high symmetry axis. And if you apply a magnetic field that is not aligned to this high symmetry axis, you sort of kill the spin initialization process, and in that way you kill your readout, right? So you get rid of your readout if there's a magnetic field that is not collinear to its symmetry axis. And what that means is that if you're looking at magnetic materials, for instance, that give rise to significant magnetic fields when you're in proximity to them, then you're sometimes unable to use the NVs because they no longer have a readout. Yeah? So this is one of the challenges, especially for studying magnetization at the nanoscale. The other challenge is that diamond is an inherently hard material to work with. And I don't mean this as a pun, but it's really hard, and its surfaces are unterminated. And that means that the surface of diamond is really unstable. It wants to make bonds. It wants to make bonds to the environment. And what that means is that you have different sources of noise in the surface that actually sort of degrade the operation of your sensor. So if you're working with NVs in diamond, if you want them to be stable, then they typically have to be distant from the surface, or you need to do very sort of particular treatments to the surface in order to avoid these sources of noise. And what that means is that you lose in sensitivity, right? The farther away you are to your target, then the less sensitive you are as well, right? So we've been looking at different material platforms that could provide analogous systems to the NV, but that could overcome these issues, right? And one of the platforms that we've been looking at, and I'm going to actually skip this. I'm going to go straight to there. One of the platforms that we've been looking at is hexagonal boron nitride. So this is also an insulator. It also has a band gap of about 6 electron volts. But now it's a layered material. It's a van der Waals material, and what that means is that its surface is intrinsically terminated, right? So you can have bulk HBN, you can have a monolayer of HBN, but it doesn't have any dangling bonds that want to be fulfilled around, right? So it has sort of intrinsically more stable surfaces. It also offers a wide variety of defects that are optically active. A lot of these defects are related to carbon incorporation into the lattice. If you think about it, HBN is almost like graphene, only you've substituted half of the carbon for nitrogen, half of the carbon for boron. So sort of structurally, it wants to have carbon impurities in it. So you can actually create a lot of different optically active defects that are related to incorporation of carbon into the material, and that are almost like organic molecules that are trapped, right, inside of this host. But also, it's very, very, because it's a van der Waals material, it's very friendly to nanofabrication approaches, right? So you can modify it very easily in order to fabricate photonic structures, but also to sort of cover different surfaces in it. So it's very friendly to actually incorporating it into different devices and so on, a lot more so than diamond. So we've been looking at these systems, and we've been looking at a particular type of defect that has optical operation around 600 nanometers. That's about 2.1 EV. So it's around the same range of where the NV operates. And we can see these defects at the single defect level, right? So that means that they're bright enough to perform sensing. So they send out a lot of photons per second, and that's what you need to have a good sensor, that your readout is very effective. And they occur sort of on MOCVD grown HBN. And recently, during my time in Cambridge, we've found that these defects also have magnetic resonances that you can read out through ODMR, so that you can read out through the photon emission. So they also have spin signatures like this. That means they are also a spin triplet like the NV. And that we can observe spin coherences in these systems also at room temperature, right? So we can do Rabi measurements, and we can see this spin processing. This measurement is performed at room temperature, so at ambient conditions, right? So they have the necessary ingredients to allow us to sort of start to explore them further towards sensing. In addition to this, these are low symmetry systems, and because of that, they have a more robust magnetic resonance signature, right? So this is an ODMR spectrum. Now you're looking at contrast versus the frequency of magnetic of microwaves that we're applying. And you can see these two resonances at zero field. That's this one and that one. But then once you apply a magnetic field that in this case is about 50 millitesla, you still sort of preserve readout of these microwave resonances, even if this field is not aligned to any of the sort of high symmetry axis of this defect, right? So it has a more robust readout, and that means it's a larger, it allows you to have a larger bandwidth in terms of where it operates well, right? So this is sort of a lot of colors to explain, but I will just go through this very quickly. What we're doing here is we're looking at contrast of each of the microwave resonances versus the angle of the magnetic field that we're applying. And what you see here is that whenever you lose contrast in one of the lines, what happens is you gain contrast in the other, right? So what that means, if you map it back out into sensitivity versus where your bias magnetic field is pointing to, what that means is that you cover almost the entire sphere, right? What that means is that your sensor operates regardless of where your bias field points to, right? You have some readout that you preserve. So I'm particularly excited about these systems, and I'll keep working on them, but also on the NV in Rio, right? The reason we're excited is because it has the necessary ingredients, right? So it's bright, it has a spin, you can do microwave spin control efficiently, and it operates at room temperature, right? So it's a good place to start, definitely. So I can't give this talk without thanking people in Cambridge who have worked with me. Hannah is a very, very talented, she was a postdoc when I arrived, and she's now in Oxford. And the students, Stephanie, Katie, Dylan, Simona, Ollie, and Eleanor have all contributed to the work that I've shown at the very end. My work there was funded by the Dutch Research Council, so I'm very grateful for them. And I hope to see you all soon. Thank you very much.
Thank you, Carmen, for this very nice talk about this huge field of research. Lots of interesting results and interesting perspectives. So are there questions? Yes?
Very nice talk, Carmen. It was a very nice talk. So I was wondering, I put in perspective what Danielle brought, which is, of course, you can reach this nanotesla, sub-nanotesla sensitivity like squids. I think they reach femtotesla, tens of femtoteslas per square root of Hertz sensitivity, but of course, you have to pay the price of being huge and etc. So given in the context of this last work, that if I'm not mistaken, you were in the millitesla range, right? Or
well, the bias field was millitesla. The sensitivity you extract is microtesla to nanotesla, so in that range.
Okay.
Yeah.
So it's still way less sensitive than squid magnetometers, but I think Hans is in the audience here. He's also working with optically pumped magnetometers. I think that's what he's promised so far. And you know, he was working in England before, and there's this trend there of using this for magnetoencephalogram images, right? And I think the optically pumped magnetometers, if I'm not mistaken, they also are in the nanotesla, low sub-nanotesla regime, right?
Yeah.
But there are challenges there too, right? So what I want to bring in is, when you look at these 2D material platforms, if you're concerned of bringing this to applications, do you see that despite being less sensitive, they could overcome the challenges that Danielle pointed earlier, that, okay, maybe they will be actually much easier to operate, far more easy to package maybe into something that could be used by industry or any other kind of, even if it's a lab controlled application, but an application that could be in the field rather than just in a physics laboratory. How do you see that? I mean,
you're absolutely right? These are not the most sensitive systems out there, and I think no one claims they are. But the advantage is exactly that. A system like this, so a microscope that has a scanning probe with an NV at the tip, you can buy commercially nowadays. and it's about this big, I think. Yeah, so it's not, and then you put in your sample, and you remove it. So it's not, it is more amenable, I think, to product development at this stage. I'm not saying it's always going to be. You can think of an optical fiber, for instance, where you put an NV, and there's several proposals out there, where you put an NV or an ensemble of NVs at the tip, and it has some microwave line, but the optical fiber itself gives you control and readout, because the control is a lot of it is optical, and the readout is all optical. So you could think of an optical fiber that can be used for endoscope, right, for endoscoping imaging, but also in drilling facilities for oil, right? So there, because of the robustness of diamond, I think, and of the solid state environment, it's easier for me, that I'm not an engineer, to think about how it could become a product, right? But from the magnetic field point of view, it's not the most sensitive probe out there. And I don't think it's going to be. You can think of ways of making it more sensitive. So if you, I mean, sensitivity always kind of looks like this, right? And then perhaps instead of square root of PL here, if you're doing pulse measurements, you have some square root of sort of interaction time times, right? So, but it always kind of looks like this. And this is given by nature. You can't really change that, right? So that's just the slope of the frequency versus whatever quantity you're trying to measure. Contrast, you can improve. So you could do, this is all with off-resonant excitation. If you do resonant excitation and you decrease the temperature a little bit, your contrast can be 100%, right? Because you're doing the same as you're doing optically. You're just reading out the population of a level, whether population is there or not. So your contrast can be 100%, or 50%, depends on how you define it. If you do resonant excitation, then that has other sort of practical limitations associated with it, right? Then you need to filter photons and so on and so forth. So you can improve a little bit sensitivity, but you're not going to get to the femtosecond, I think, regime. It's how for applications where you don't need that sensitivity, how does this make your life easier? Yeah.
I would want to comment on this idea. Okay, sorry, just because it's on this question about sensitivity. I'm trying to remember the person that said that from ICFO in the quantum optics now in December, and he showed a very interesting graphic about that he didn't understand about a kind of limit that you could not pass about sensitivity for measuring magnetic field and also resolution, spatial resolution. It seems that there is like a trade-off between resolution, so you are not that sensitive, but you resolve better, and maybe your resolution is bigger. It was like theoreticians were trying to understand this. Now I don't remember the reference, but yeah, just quickly.
Of course, we can discuss later that, but just do the comment on that. When the most important thing here is in which scale are we looking for that kind of sensitivity, right? So atomic magnetometers are very good at the scale of 1 centimeter volume, right? But when it comes to nanoscale or micro scale, then you guys are like the best sensors. Then the question is at that level, and of course it comes with the resolution. So at the centimeter scale, magnetometers are very good. Atomic magnetometers are very good. But at the nanoscale, then you can have these maps of magnetic fields, which is why the MV centers gain so much attention because of that, right? But in that respect, even in the of course we are not going to compete with big scales, but in that nano scale, how the last works you show the sensitivity, how good is it compared with other works with which they show these maps of biological systems and all that? Because when you do measurements by contrast, also you don't have like real-time measurements of magnetic field. Is it possible to get
No,
real-time measurements?
it's mostly integrated. You can do single-shot readout of NVs, but then again, we go to another type of experimental sort of setup that you need. So it's mostly time integrated. What you can do is sort of delayed from a stimulus, right? So what I showed of the neuron measurement there, it's a stimulus that is given repeatedly, and then you measure a delay from that stimulus. That's what you can do, but you're always still averaging in time.
Okay,
Yeah. And then...
So then how is the bandwidth of that detection?
Sorry?
How is the resolution in time, in the sense that how long it takes a measurement, or?
Well, it's the same as measuring, yeah, well, in these systems, when I showed the Rabi measurements, right, that's not measured in a single shot. I give a stimulus, which is this microwave, and I control that delay. So I control how long that interaction lasts for, and I perform my measurement at the end, and that's what your timing resolution is. But ultimately, you could integrate forever. So you can enhance your sensitivity, the quantity that you're measuring, but you're still integrating for a certain time, right? It's still an integrated measurement. And then in terms of spatial resolution and field resolution, I think spatially, the only thing that has similar resolution to what the NV can achieve is nanosquids, right? Nanosquids nowadays, you can put them at the tip of a scanning probe as well. So the figure I showed, the image I showed at the very beginning, that's a scanning probe, basically, with a squid at the tip. And then you can reach a couple of nanometers of resolution. So you can do that. And then they are very sensitive in terms of what magnetic field they can sense, but they need to operate at cryogenic temperatures, right? So there's always one trade-off that you need to, you need to overcome. Yep.
So maybe I'll just ask if there's some questions at the Zoom. Otherwise, okay. So maybe we thank Carmen again, and then we keep the other questions for the discussion this afternoon, and then we go for the last speaker of the session, which is José Inácio da Costa Filho. Thank you. I think you need to.